We want to talk about Taylor series and Maclaurin series. We'll start with Taylor series. Before we get into actually what that says, let's think of a function that's given by our power series. We expand this, we get that. Now, if we do f of a, all of these terms will be zero. So we're only left with this c naught. Now, if we take the derivative, we're going to get c1 plus 2c2 x minus a plus 3c3 x minus a squared, and so on. And now if we plug in a for this, just like before, all of these disappear because they're zero. We're left with c sub 1. We'll get 2 c sub 2 b x minus a plus 12 c sub 4 x minus a squared, and so on. Once again, plugging in a, we're only left with this first term. So by doing all these derivatives, we can come up with a that's going to use derivatives to give us our c values. What this turns out to be is this c sub n is the nth derivative at a divided by n factorial. So we get 2 here, that is 2 factorial. Here is 3 factorial. Once we multiply this 2 over with another derivative, 24 is 4 factorial. And so if we were going to get our C2 by itself, we would there's a theorem related to this. It says that if our function f of x has a power series representation, or power series expansion, however you want to think of it, at some value a, which means if we can rewrite our function in this manner, as long as our x minus a is less than our rho value, our radius of convergence, then E sub n can be written this way, with our nth derivative at a divided by n factorial. Now the factorial is good. All right, so we're going to be able to do this if, so any power series will be able to be written with this. So our overall setup is going to be our f of x equals, oops, not that. We want x minus a, the n. Oops, sorry. And up here, since it's centered at a. All right. So if we write this all out, we're going to get just f at a. So whenever n equals 0, we're going to treat this 0 derivative as our normal function, and 0 factorial equals then our first derivative over 1 factorial, which is just 1, plus our second derivative over 2 factorial, and so on. Is called our Taylor series. Formally and completely the Taylor series of a function at a, or it could be about a or centered at a, whatever. But it's our Taylor series. Now, if our a value is specifically 0, that's going to give us what's called Maclaurin series, where our f of x is going to be the summation of n equals 0 to infinity of our nth derivative at 0 divided by n factorial. And since our a is 0, it's just x to the n. So a equals 0. Make life a bit easier. The Taylor series aren't too bad to deal with, but Maclaurin series, since it's only x and not x minus something, just makes life a whole lot easier. So let's go ahead and do an example of this. Let's find the Taylor series expansion for e to the x, and then find our radius of convergence as well. So process for doing this, we are going to need a bunch of derivatives. So let's find all of those derivatives. In this case, they're all the same thing. Then we need to evaluate all of these functions at our a value. Since this is a Maclaurin series, our a value is going to be 0. And so they're all just 1s. So using our equation, it's a 1 because that's all of our derivative values over n factorial times x to the n. Or if you want to simplify this a bit, x to the n over n factorial. Now, let's go ahead and check for our radius of convergence. So we're going to do a ratio test. Got the c's on this factorial because we need that whole n plus 1 to be have the factorial applied to it. doing our division. X will simplify, factorial will simplify, and now x divided by n plus 1 as n goes to infinity, this is going to 0. So our radius of convergence is going to be infinity because any x value is going to work. So that's nice. Now, when we do these, we have our overall function for our Taylor series. This is our standard way of applying it. But we can't always do an infinite summation. So we're going to find what's called the nth degree of f at a, or centered about a, or about a, however you want to think of it. Now we're going to call this a t sub n, and it's going to be a function of x. And this is going to be our summation of I equals 0 to n. So partial sum of the I derivative of f at a over I factorial times x minus a to the I. So figuring this all out, we get our function at a plus our derivative at a over 1 factorial x minus a plus. And then we keep on going until we get to the nth derivative. And we're going to stop there. And now our overall function is going to be this Taylor series polynomial plus whatever that remainder is. Because this polynomial is only give us some of it. We still have the rest of this stuff that would need to be there in order to complete our overall polynomial. So what we also know is that the limit as n goes to infinity of this r sub n of x has to equal 0. Just like if we would do the limit of our polynomials, we would get f of x. And this, of course, is going to be for, so we're within our radius convergence. And building off of this, there's something called Taylor's inequality. That says if the absolute value of the n plus 1 derivative of x is less than or equal to m for our x minus a being less than some value d. So it means if we can restrict our x's to a certain amount, so they're close to a, if that restricts the n plus 1 derivative so that it's bounded. It can't go above a certain thing. It's not going to go off to infinity. Then our remainder, that r sub n, satisfies this inequality, that its absolute value will be less than or equal to m over n plus 1 factorial times x minus a raised to n for that x minus a being less than or equal to d. And it was or equal to up here as well. Which means that our remainder is basically limited by the next derivative. Whatever that derivative is, or the next term really in our Taylor series. Find a few more of these Taylor series. Now, the one we just did, e to the x, for our Maclaurin series, we said was this. That means a new way of writing e, our x is 1. So this is 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, and so on. And now e is roughly 2.718. Right there's your 2. So the rest of this adds up to about 0.718. So now let's do this same thing. Well, let's not do a Maclaurin series. Let's do a Taylor series, but we want our a to equal 2 and our function to be e to the x. So how does this change things? So we're still going to do the same thing we did before of make our list of all of our derivatives. And then plug in our a value. Now our function, whenever we write it, is going to be e squared on top x minus 2 to the n. So things change when you change your A value. We will get similarities, and you'll see some things that are going to show up again and again, but there will be slight nuances and slight differences. So be careful of that. Let's go ahead and take a look at a couple of the other values that we, or the other equations that we're going to get for our Taylor series. Or let's do Maclaurin series specifically. So let's do our function equals sine. And since Maclaurin series, our A is going to equal 0. This one will give us cosine. This one's negative sine. This one is negative cosine. And then our next one's going to get back to just sine. So we have a nice repetition. F of A, sine of 0 is 0. And I can plug just 0 in there. This will be 1, 0, 1. So when we're writing out our summation, it's going to be 0 plus 1 over 1 factorial times x minus or plus 0 plus negative 1 over 3 factorial x cubed plus x to the fifth. And we keep on going. But notice all are left with the odd terms. Now we don't want to put any notation on our ends down here that it only has to be odd. We want to be able to use all of our ends without skipping anything. So a way we can do this is notice how we're switching from positive to negative to positive. So it's like an alternating series. So we can go ahead and do that. But now let's reimagine our numbers in our numbering system. Let's call this our 0 term. There's our 1 term. There's our 2 term. Now, equals 0 to get a 1. N equals 1 to get a 3. N equals 2 to get a 5. So we're always getting odd numbers. So in order to get an even number, you can multiply something by a 2. So 2 times something is always even. To make that odd, we can add a 1 or subtract a 1 or add a 3 or subtract a 3 or add or subtract any odd number. In this case, whenever n equals 0, we specifically want 1, so we want to use the plus 1. And our exponents follow along as well. And right here is the Maclaurin series expansion for sine. Let's try cosine just to get a practice. We're going to have something similar to what we just did. Since we're going through the same functions with our derivatives, just in a different order. And then plugging in 0 for our Maclaurin series. We get 1, 0, -1, 0. So now, unlike the last one, we were getting our odd numbers. Here, we're only getting the even numbers. We're still alternating between positive and negative, starting with a positive. So we're going to do -1 to the n. But now we want the even numbers. So we just can do our 2n for our exponent in factorial. Again, make sure inside that factorial or that factorial that we have parentheses to show the n, the factorial part applies to the whole thing. And your radius of convergence for all of these is going to be infinity over the sine cosine, just like the exponential. Now let's do our sine again. But let's use, say, pi over 2 as our a value, not x, a. And let's see what happens. So take all your derivatives. And then we're plugging in pi over 2. So this time we get a 1 there for our initial function. That's a 0. -1. We're keeping the even terms. So we still have our -1 to the n. It's a 2n on the bottom that's getting the factorial. But now it's not just x, it's x minus pi over 2. And again to the 2n power. So again, whenever we do a general Taylor series, depending on what it's centered at, it can modify things a little bit. You'll get something that's similar to what you dealt with the Maclaurin series, but there'll be nuances that make it change. All right, next up. There's a thing called a binomial series. Which is 1 plus x to the k power. And whenever we do our we end up with this. This is probability and statistics. It's k things choosing n. And so what this gives us, and then times our n, or excuse me, x to the n. Now, what does this thing mean? That is, we're going to take our k minus 1, k minus 2, And we're going to keep on multiplying until we get down to k minus n plus 1, all divided by n factorial. Think this is on top we have, whoops, k factorial. And then on the bottom, it's our n factorial times k minus n factorial. So it's kind of a long, drawn out, cumbersome thing because whenever we do our expansion of this, if we would cancel this, we would stop at the one right above it. So k minus n plus 1. So however you want to think of it, there's our binomial expansion. On this one, our row, so this will only work for x's that fall between -1 and 1 with that. Now you can do this for any function. Those are your is arctangent. Is n equals 0 to infinity of -1 to the n n plus 1. Be careful, this bottom no longer has the factorial with it. The natural log of 1 plus x to the n plus 1, or n minus 1, doesn't really matter, x to the n over n. So again, this differs from our exponential that we now have this alternating part and the bottom is not a factorial. And then we just did our binomial. And so that you can just go through the basic formula for a Taylor series or Maclaurin series, take all of your derivatives, and then everything else like that. So some of them are not quite so easy. Some of them are a little more drawn out. Finding that pattern to come up with your C sub n and simplifying it into something along these lines is not always straightforward, but there are ways you can work around and at least something down, even if you're writing it all out. Now, if we are going to multiply or divide these power series, sometimes it can be a little bit difficult to do this process. So say we were going to do a function that is e to the x sine of x. Multiply our individual Maclaurin series. And we'll say here a equals 0 to establish its Maclaurin series. But now what we can do is multiply out, or actually evaluate these, do our summations. So 1 plus x squared over 2 factorial. And you can put this one over 1 factorial if you wanted to. Plus x cubed over 3 factorial, so on. Then do the other one, where it's going to be x over 1 factorial minus x cubed over 3 factorial plus x to the fifth over 5 factorial, and keep on going. Application on this, I don't, because there's more than a binomial, but it's our multiple distribution type thing. And then you can combine all of your like terms for this and then get a new equation. Similar thing if we wanted to do a tangent, not arctangent we did before, but just tangent. We could write it as a sine over cosine. We can then write our individual do our division. Our polynomials that we're getting, and at least the first couple terms you would get this. That's being established, and maybe come up with another equation for your C sub n's, then that you could then write as a simple summation. But the key here is using your older stuff to find newer information. But remember what your original basic formula is for the Taylor series. 0 to infinity of the nth derivative evaluated at a divided by n factorial times x minus a to the n. Maclaurin series is nothing more than a specific case of your Taylor series where your a happens to equal 0 specifically. Makes life a little bit easier, and we have our common formula for like the e and the sine and the cosine specifically, but know how to do it the long way by hand to how to get them. If you know the shortcuts and what those equations are, it's nice to double check yourself. We can then use those to then evaluate things. You could also use your common Maclaurin series or Taylor series, then do integrals or derivatives. You could also plug in different things like sine of 2x or cosine of 3x or something like that. So you need modifications off of the different equations that you already know to save you from doing them the long way.